Hello. Hello everyone. Welcome to the course Semiconductor Devices and Circuits. This is the live problem solving session for week 3 of the course. I am Mayank. I am a research scholar in the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Sanjeev Sambandhan, who is a professor in the Department of Instrumentation and Applied Physics at ISC Bangalore. The course plan for week 3 is density of states, Fermi function, carrier concentration, and doping. This live tutorial session is being held every Sunday 6 p.m. to 8 p.m. at the Google Meet link. So first we will do lecture recap of the top this week's topics. So last week we studied about mobility. So mobility gives you defines the speed of the carrier. You so mobility defines the drift velocity, which gives you the speed of the carriers. But the current values or the current density is a combination of both speed and quantity. So speed is defined by mobility or drift velocity, and the number is defined using carrier concentration, that is n small p. So now what is carrier concentration? So you can understand this by this figure. Uh, so to count the carriers, we must first count the available chairs they can occupy. Uh, the density of states answers this fundamental question, and it is defined by the number of solutions to Schrodinger's equation that exist per unit energy per unit volume. So here, let's assume this is a classroom with uh, let's say 50 chairs. So the number of chairs is equivalent to your density of states, which is the number of seats available for electrons. Then it's a probability of a student sitting on a particular chair, which in terms of electrons is defined using Fermi Dirac distribution. That multiplication of those will give you the total number of students, which is what is your carrier concentration. So the density of states is derived using conversion from momentum space to energy distribution. So first you have the grid, which you are defining number of states per unit volume in K space. Then then you are then you are figuring out how many states between K and K plus dk, which is incremental number of momentum. Then you convert that to energy. So you which gives you the number of states between energy E and energy E plus dE. And then you normalize it to your physical unit volume, and then you normalize it to the unit energy dE, which gives you the density of states. So first we start with K-space grid. So the momentum is quantized into discrete points. Each point is a valid state shared perfectly among 8 adjacent spatial cubes. So volume of one cell in K-space is given as pi q by Lx Ly Lz. Then you have then so we know that in uh, in electrons there are two spin states, spin up, spin down, and each energy state can have a spin up or a spin down particle. So we multiply it here. So we multiply 2 here. Then each state is distributed among 8 cubes. So we divide that 8. So from there we get Lx Ly Lz divided by 4 pi cube. Then we, so this was in this, when we go to 3D case, large amount of case, we talks in terms of spherical shell instead of cubes. So if we keep K constant, the locus of all valid quantum states forms a sphere in 3D K space. So we calculate the total states residing within a thin spherical shell of thickness dk. So the volume of the thin spherical shell will be 4 pi k square dk, and we calculated the number of states per unit volume as Lx Ly Lz by 4 pi cube. So this will give us the number of states per unit dk. Now we convert it to energy. So energy we know is h bar square k square by 2m, and k square is 2me by h bar square, and this gives us k as 2me half by h bar, and when we do d by de, we get dk is 2m half by 2 h bar e minus half de. So now from here we can calculate our density of states. G of E de is Lx Ly Lz by 4 pi cube 4 pi k square dk is equals to this value. So which gives us Lx Ly Lz 2m cube power half e power half by pi square h bar cube de. So now we normalize it. To find the true density of states, we divide the physical volume of the material and the specific energy interval. This reveals that in 3D available scales precisely with the square root of energy. So we divide by physical volume and we divide it by dE. So this gives us the number of density of states as 2m cube per half by pi square h bar cube into e per half. So we see that energy is the density of states is proportional to square root of energy. And if we plot it, we get so in a perfect city crystal, there are no states, that is no chairs in the band gap. Above the conduction band and below the valence band, the number of available states increases as the square root of the energy deeper into the band. So we take the conduction band minima or the valence band maxima as the 0th energy point, and from there we go deeper into the band. Next. So this till so right now we studied for 3D 3 dimensions. So if we change the dimensions to 2D, the so what is 2D material? So 2D material is when so when a material is significantly white but atomically thin. So in 2 dimensions it is macroscopic, but in 1 dimension it becomes atomically thin. That is the number of it becomes a potential well. So we apply this exact same 5 questions, but our spatial constants drop from 3 dimensions down to 2 dimensions. So from Lx Ly Lz it becomes Lx Ly. So so when we calculate this, we get n of E is equal to m by pi h bar cube h bar square. So you can see here it does not depend. It is not depending on energy. So in 2 dimensions, the density of states are constant for a particular band of energy. So when we apply one solution is shared by four squares, so that gives us the Lx Ly by 2 pi q square. The it will be a circle here, so the circular decay area will be 2 pi k dk, and when you translate it there, we get n of equals to m by pi h bar square. So you can see here, so we replace k by this formula and dk by this formula, which would, so this will remain the same as before. You can see it's here, it's e power half. Here it's e power minus half, so this will cancel out this. Here it's 2 m power half. Here it's 2 m power minus half. That will also get cancelled out. Uh, So when we normalize by area and by dE, we get m by pi h bar square. So the energy is at constant, so it's a constant. So you can see here, unlike 3D materials, the density of states in a 2D material does not scale with energy. It behaves as a step function. Once you cross the band edge, the number of available states is immediately and eternally constant. So our goal is counting free carriers. So we just saw that. So we had studied that the carrier concentration given as a function, as a multiplication function of density of states and Fermi function. That is how many seats exist for electrons to occupy into what is the statistical likelihood an electron is sitting in a seat. It gives us total number of electrons available for conduction. So we studied about density of states. So in 3D material, n of e is proportional to e power half. In, in 2D materials, n of e is proportional to e power 0, that is constant. In 1D material, n of e is proportional to e power minus half. And in 0D material, n of e is proportional to 2 delta e, that is, it is 0 everywhere except at band edges. So we are only focusing on 3D bulk semiconductors which are governed by e power half behavior. So in 3D, the conduction band has Nc of E proportional to E minus Ec power half, and in valence band we have Nv of E proportional to Eb minus E power half, and in the middle we have Eg, forbidden gap of length Eg, where density of states is 0 in a perfect crystal. Next we come to Fermi derived distribution. So electrons are fermions. They obey the Pauli exclusion principle, that is, no two identical fermions can occupy the same quantum state, and their behavior is governed by the Fermi derived function f of e equals to 1 divided by 1 plus e power e minus ef by kt, where f of e is probability of an energy state E is occupied by an electron, ef is the Fermi level, which is the critical energy threshold, k is Boltzmann constant, and T is temperature in Kelvin. So, so if you see here, so if you see here, if my T at 0 Kelvin, that is at T equals to 0, uh, the, if E is greater than EF, then this will become E power infinity. This will become E power infinity, which uh, so that will make it 1 by E power infinity, that is 0. And if E is less than EF, this will become E power minus infinity, which is 0. So this will become 1 by 1 equals to 1. So at 0 Kelvin, if energy states less than Fermi level, the probability of electron is 1. And if energy is greater than Fermi level, the probability of electron is 0. So the Fermi level is defined as the energy value below which all the states are occupied and above which all the states are empty at absolute 0 or 0 Kelvin. So now we again understand this with an analogy. So let's assume the physical shape of the bucket represents the density of states and the volume of water represents the total number of electrons. So the exact surface level of the water at absolute 0 is the Fermi level. So that everything is below this level, there is nothing above. So at T greater than 0 Kelvin, thermal energy causes water molecules to splash into the air above the surface. This is called thermal excitation. So when you give some temperature more than 0 Kelvin, electrons are coming out from the Fermi level and occupying higher energy states, and that would mean reduction of electrons in energy states below Fermi level. So as you increase the temperature, you go from a step function to a smoother function, which you can see here. So at 0 Kelvin, it was step function like this. So your probability is 1 till energy EF 0, and above that it's your probability is 0. So but as you increase temperature, it gradually becomes a smoother function. So at T equals to 0 Kelvin, it was perfectly step function, 100% occupancy below EF, 0% above. And as the increase the temperature, the function smooths out. But regardless of temperature, the Fermi level always passes through a probability of half at exactly E equals to EF. So when energy is equal to EF, the probability is always half. And if you see here, as you increase the temperature, the function smooths out more and more. So at T equals to 0, it's like this. At T equals to 1, it's like this. At T equals to at T2 greater than T1, it's like this. So the Boltzmann tail. So when the energy level is significantly higher than the Fermi level, E minus EF greater than 3, the plus 1 in the denominator becomes negligible. So f of E is greater than 1 upon 1 plus E per E minus EF by kt. So when E minus EF becomes greater than 3 kt, that is E becomes E per 3, which becomes higher order of magnitude than 1. So the 1 becomes negligible. So we can just write 1, ignore the 1 and write it as 1 upon E per E minus EF by kt, and or take it to the numerator as E minus EF by kt. So in the conduction band, the Fermi-Dirac probability decays exponentially, exactly mirroring the classic Boltzmann distribution. Now, so we studied the probability of electrons. Now, what about the probability of holes or vacancies? So electron means the state is occupied, but hole means the state is empty. So if electron, the state of occupation, probability of occupation is given by f of e, then probability of empty is given by 1 minus f of e, because occupancy is a binary coin toss. Either there will be either the state is occupied or it is empty. Hence, the probability will just be 1 minus f of e. So you can see here the density of states is like this, whereas the Fermi function is given like this. For electrons is f of e, for holes it's 1 minus f of e, which is given by like this. And so so carrier concentration is given as the multiplication of both of them, and when you multiply both of them we get a small, only a small overlap region. So carriers only exist when both states are available and the probability is non-zero. So which becomes so this much area for n of e and this much area for p of e. So summing the conduction band, to find the total electron concentration n naught, we sum every electron in every energy stage dE from the conduction band h ec to infinity. So n naught equals to integral ec upon ec to infinity f of e n of e dE. So effective density, by applying the Boltzmann approximation and integrating all states in the conduction band, can be mathematically squashed into a single effective density of states, that is NC, sitting exactly at EC. And then we can use, using this NC value, we can apply the Boltzmann approximation to get the uh, density at any E value, which will be given as n equals to NC E minus EC minus ER by KT, where NC is effective density of states in conduction band and EC minus ER distance of Fermi level from the conduction band. Similarly, for holes, we can write P equals to NV e power minus EF minus EV by KT, where NV is effective density of states in valence band and EF minus EV is distribution distance of Fermi level from the valence band. So this makes the Fermi level as the master level. Because the carrier equations are exponential, tiny shifts in the Fermi level drastically alter the material properties. Move EF closer to EC, free electrons increase exponentially. Move EF closer to EV, free holes increase exponentially. So the takeaway here is, by controlling the position of Fermi level through doping or voltage, we control the flow of current. This is the foundational mechanism of all semiconductor devices. So this is how the semiconductors work. So we change the position of Fermi level through doping or voltage, which is used to then change the amount of current flowing. And this is exactly how semiconductor devices work. So next we have visualizing carrier concentration, doping, and Fermi level. So we studied that density of states and Fermi function gives us the carrier concentration, which looks like this. And integration of the product over the band edges yields the exact number of electrons and holes per unit volume. So now we come to intrinsic carrier concentration. So what? How do we get a carrier intrinsic carrier generation? So how carriers are generated intrinsically without any doping or application of voltage or light. So physically what happens is, let's say you have pure silicon or 2D silicon lattice, you can see here, uh, and uh, it is sitting in dark at temperature T. What will happen is that an electron from the silicon will get thermally excited, leaving behind a hole, which you can see in the energy band diagram. Electron gets excited from valence band to conduction band. So this gives us the rule n equals to p equals to ni, which is intrinsic carrier concentration. And for pure silicon at 300K, ni is roughly 1 into 10 per 10 per centimeter cube. This value is debatable actually. So some place you will also, some at different places you will see different values ranging from 1 into 10 per 10 to 1.5 into 10 per 10. So the intrinsic carrier concentration. So the equation is depends on the universal constant Nc and Nv for a particular temperature. So Nc and Nv depends on universal constants and effective masses of electrons and holes. Then you have Eg, which is the barrier gap. So as E naught increases, as Eg increases, Ni decreases. A wider gap requires higher temperatures to promote an electron. Therefore, there will be lesser thermal excitation, so Ni will decrease. And then you have Kt, which is temperature. So as you increase the temperature, your Ni will increase. So as long as Nc, Nv, and Eg remain constant, Ni square is a fixed powerful diagnostic constant at a given temperature. So if we are not changing Nc, Nv, or Eg, which generally don't get changed in a typical material, ideal material. So this gives us Ni at constant at a given temperature, and this Ni can then be used for multiple solving multiple parameters. So if effective mass of holes and effective mass of electrons is equal, then Nc equals to Nv. That makes it the, so EI is given using the use has a equation Kt by 2 ln Nc by Nv. So if Nc by Nv are equal, then it becomes ln1 0. This means this value is 0. So that means EI is same. Your intrinsic Fermi level is same as your mid gap, which is EC plus EV by 2 or EG by 2. Uh, if NV greater than NC, EI becomes higher. If NC greater than NV, EI becomes lower, that is closer to valence band. So the position of EI, which is intrinsic Fermi level, is determined by the balance of effective masses or density of states for electrons and holes with a thermal energy term influencing the offset. So now we come to doping. So so EI is your baseline, which is intrinsic. So electron count equals hole count. Now, if we do N-type engineering, that is, we increase the number of electrons in the conduction band, we change the Fermi level to EF, which is upwards closer to conduction band. So EC minus EF will decrease, and which will mean N carrier concentration of electrons small n exponentially increases. So only if we do P-type engineering, which is we increase the number of holes, then EF will snap downward, that is closer to valence band. EF minus EV will decrease, and number whole carrier concentration will exponentially increase. So doping allows us to purposefully tilt the scale. We manipulate carrier populations by relocating the Fermi level away from the intrinsic baseline. So the mechanism of ionization. So you can ionization can happen when a fifth electron inserts. Then there will be thermal breaking of electrons inside the lattice, and that will result in separation of the electrons from the lattice, resulting in a extra negative mobile carrier. The nucleus positive charge is no longer balanced by the electron cloud. A neutral addition creates a fixed ion and a mobile carrier. So how is doping done? So if we want to increase electrons, we give donors like phosphorus, which have five valence electrons. If we want to increase holes, we give acceptors with like boron, which have three valence electrons, so one less than silicon. So they would like to have an electron from silicon, whereas phosphorus has five electron atoms, so they will like to give one electron to silicon. So that is why generally we use group 5 for donors and group 3 for acceptors. So, donor doping adds an extra electron, acceptor doping adds an extra hole, and this will leave the leave behind a positive ion on the phosphorus, and that will leave behind a negative ion on the boron. And accordingly, the Fermi level will shift towards conduction band or valence band. So we know N is given as N is given as Nc into E power minus EF, Ec minus EF by kT. So if we reduce the value of Ec minus EF, then N will increase very much. So to increase gap, total exponent gap must become a smaller negative number. So hence we are reducing the by making the value of EF closer to conduction band, we are reducing Ec minus EF, which will effectively increase the value of E power minus Ec minus EF by kT, and this will increase the value of N. So decreasing the gap between Ec and EF exponentially explodes the electron population. This is the material energy of an N-doped semiconductor. Now we come to charge neutrality equation, which is given as P plus Nd plus equals to N plus Na minus. So your P and N are free carrier concentrations, whereas Nd plus and Na minus are ionized atoms left behind in the matrix. So, we do not disturb charge neutrality. Every added mobile carrier is perfectly counterbalanced by a fixed immobile ion left bound within the lattice grid. So the rule of effective doping, if in, so let's say we give both donors and acceptors inside the semiconductor, then both will be pulling the Fermi level towards themselves. So the effective doping will be if Nd greater than Na, the material behaves as N type and the effective concentration will be Nd minus Na. Whereas is Na greater than Nd, the material behaves as P type and the effective concentration will be Na minus Nd. So you have pure intrinsic silicon where there are no additional atoms, no doping, everything is silicon. Then you have fully compensated silicon where you have given equal amount of acceptor doping and donor doping. So the silicon is not pure; it is full of donors, but the number of acceptor donors and number of acceptor dopants and number of donor dopants are equal, which means N equals to Nd. So the Fermi level does not shift; it stays where it was. So it's similar to intrinsic silicon, but it is actually compensated. So complete compensation when N equals to Nd, the opposing forces perfectly cancel. Despite being riddled with impurities, the material behaves exactly like pure intrinsic silicon. The balance is restored. The Fermi level returns to the intrinsic mid-gap position, indicating equal concentrations of mobile electrons and holes, regardless of the high total doping concentration. So we studied that in, when you have N-type doping, it increases carrier concentration. The Fermi level must move closer to conduction band to reflect this abundance. For P-type doping, it increases hole concentration. The Fermi level must be pulled towards valence band. Then we can have non-degenerate doping, where the Fermi level crosses the Boltzmann approximation range, which is 3 kT. So at room temperature, the thermal energy kT is approximately 0.025 eV. The 3 kT boundary is roughly 0.075 eV from the band edges. Degenerate doping, if extreme doping pushes EF into the 3 kT zone, that is EC minus EF less than 3 kT or EF minus EV less than 3 kT, standard Boltzmann approximations fail. So we exclusively calculate for non-degenerate semiconductors where EF remains safely within the central band gap. So we generally do not calculate for degenerate semiconductors where the Fermi level crosses the 3 kT threshold. So now we come to traps. So in a perfect crystal, a pure silicon lattice has no defects, resulting in an entirely empty band gap with no isolated energy states inside. So when we introduce impurity, adding a donor with 5 valence electrons disrupts the balance. 4 electrons bond perfectly, the fifth is loosely bound. This isolated positive charge in wandering electron creates a specific trap state directly inside the previously empty band gap. So in terms of hydrogen, so the donors ionized positive core and its fifth electron act exactly like a basic hydrogen atom. However, because this atom exists inside a silicon lattice rather than a vacuum, its binding energy shrinks drastically. So in vacuum, it would be 13.6 eV, similar to hydrogen. But inside the lattice, the binding energy would be 13.6 eV by ER square into me star by m naught, where me star is the electron's effective mass changed due to lattice, and er would is 11.7, which is silicon's relative permittivity, which is heavily shielding the charge. The result is that the energy needed to free the electron dropped from a massive 13.6 eV down to less than 0.1 eV. So the power of room temperature. So the intrinsic barrier in pure silicon promoting an electron requires a full 1.12 eV band gap is difficult. At 300K, only a tiny fraction makes the jump. But you have a donor level which is less than 0. The newly created donor trap sit mere fractions of an electron volt away from the conduction edge, which means the basic thermal energy at room temperature easily provides the less than 0.1 eV required to snap the fifth electron away from their donor atoms, ionizing them and flooding the conduction band with free carriers. So this requires redefining carrier concentration. So N equals to Nc e power minus Ec minus Ef by kT. So then we replace it with N equals to Nc e power Ec minus Ef by kT into e power Ec minus Ei into Ef minus Ec minus Ei into Ef minus e power Ef minus Ei. So this part is identical to Ni, so that will make it N equals to Ni e power Ef minus Ei. This elegant new equation perfectly tracks the physical reality. The electron count N is dictated entirely by how far the new Fermi level has moved from the intrinsic center. So this gives us mass action law. So we can we got N equals to Ni e power minus Ef minus Ei by kT. Similarly, if we calculate for P, we get Ni e power minus Ef minus Ei by kT. And if we multiply both, the exponential part cancels out and it becomes N into P equals to Ni square. So regardless of how heavily a semiconductor is doped at thermal equilibrium, the product of free electrons and holes is always rigidly constant. So if we know the majority carrier count, you instantly know the minority carriers count also, as they perfectly balance each other out. That is P equals to Ni square by N. So you can visualize it. The density of states is the so because EF is the dead center, the probability curve dictates the number of electrons equals the number of holes, that is N equals to P equals to Ni. But as EF shifts towards the conduction band, so adding donor shifts EF up, the entirely probability curve EF is dragged up with it. So this results the probability of finding an electron in conduction band skyrockets, that is N greater than Ni. And because of this curve, shifting of the f of e curve, the because the curve moved up, the value of 1 minus f of e, the probability of finding a hole plummets. The whole population is statistically suppressed. And if you similarly, if you bring EF closer to EV, then the holes will dominate and the electrons will get suppressed. So in intrinsic, the level is centered. Fermi level is centered at EI mid gap. Then it shifts For n-type, it shifts towards EC. For p-type, it shifts to EV. The majority carriers in n-type is electrons, and in p-type is holes. And at thermal equilibrium, we also assume that turn on microphone access to talk. At minority, so the at thermal equilibrium, we assume that the number of uh, free electrons is almost equal to the number of ionized donors, or number of holes is equal to number of ionized acceptors in p-type, and the minority carriers can then be calculated using p equals to na square by n, or n equals to na square by p. So the mass action law n equals to p into na square applies to all systems at thermal equilibrium. So now, we see the effect of temperature on carrier concentration. So we see here, this is the curve of n by nd divided by temperature as a function of temperature. So near the room temperature or around the room temperature, you see that the value of n by nd is approximately 1 and it does not change. So this is the engineering sweet spot where n matches engineered nd. So nd is what you engineered by doping, and n is what you have as free carrier concentration. So near the center, you have it around constant, but as you decrease the temperature, you see that n decreases a lot, and this is called freeze out, where there is not enough thermal energy to thermally excite the electrons, and as you increase the temperature a lot, you see that n increases exponentially. So this is the region where the intrinsic concentration is dependent on temperature. So this is the region where the intrinsic carrier concentration overtook the amount of doping done, and uh, so hence the number of electrons is also increasing with intrinsic carrier concentration. So why does doping only control the semiconductor within a specific temperature plateau? So absolute zero, the thermal freeze out. So at T equals to 0 K, zero thermal energy exists. Electrons lack the energy to escape the clutch of the donor atoms. So the semiconductor acts as a perfect insulator. Then at some temperature, you have partial ionization where, so because the donor gap 0.1 eV is drastically smaller than the lattice gap 1.1 eV, slight heat selectively promotes donor electrons while valence electrons remain trapped statistically. And then near the near room temperature, you have all the donor atoms are ionized, as well as some electrons from the valence band are also ionized. So the intrinsic contribution is statistically invisible compared to the donor contribution. So N total is approximately equal to ND. So which means the semiconductor's conductivity is 100% dictated by engineered dopants and not by the base silicon itself. So now when you go even higher temperatures at high heat, the sheer volume of silicon atoms overpowers the dopants. The material reverts to acting like a pure semiconductor, destroying the engineered device control. So when you get very high temperatures, all the uh, electrons from the valence band shift to the conduction band, resulting in massive amount of electrons in the conduction band, massive amount of holes in the valence band. This results in Ni dominating over the Nd. So the N total becomes equal to Ni, which is greater than Nd. So like donor atoms available were 10 per 15 per centimeter cube, whereas silicon atoms available are 10 per 21 per centimeter cube. So there are four thermal regimes for doped silicon. At T equals to 0, it's called freeze out, where there is no electron source, and dopant status is 100% neutral, and N is equal to 0. And then there is partial ionization, where donors are the main electron source and it is partially ionized, and N is less than Nd. Then there is around room temperature, silicon acts as an extrinsic semiconductor, where the dominant source is still donors, but they are 100% ionized, resulting in N equals to Nd. Then when at a very high temperature, the semiconductor comes back to acting like an intrinsic semiconductor, where the dominant electron source becomes valence band. The dopants are still 100% ionized, but they are not doing anything now because N is now greater than Nd. So the macroscopic rule is charge neutrality, which is P plus Nd plus equals to N plus Na minus. So despite localized ionization, the entire semiconductor block remains perfectly charge neutral at all times. To solve this, we must precisely count the fixed ionized components Nd plus and Na minus. So calculating ionized donors, Nd plus equals to Na Nd, which is total number total available states, into subset of empty of electrons. That is probability a state is full f of E equals to Ed, and probability a state is empty 1 minus f of E equals to Ed, which gives us Nd plus equals to Nd divided by 1 plus Gd e power minus Ed by minus Ef by Kt, where Gd is your donor degeneracy factor. So normal states allow two electrons spin up and spin down, but a donor state allows only one. Therefore, Gd equals to 2 is injected into the denominator. Similarly, for calculating ionized acceptors, the function will be Na minus by Na equals to 1 divided by 1 plus Ga e power Ea minus Ef by Kt, where Ga is your acceptor degeneracy factor. Now, when it comes to holes, we have two distinct EK diagrams. One is for light holes and one is for heavy holes. So, and then again, each state is having two two electrons, which is two quantum states, that is spin up, spin down. So now we have four states here, two for light holes and two for heavy holes. So the correction factor here will be 4 instead of 2. So the donors give up an electron, acceptor capture an electron. Donors have fixed positive fixed score, acceptors have negative fixed score. And donors promote to conduction band, acceptor pull from valence band. Donors have 2 Gd equals to degeneracy factor as 2 electron spin. Acceptors have degeneracy factor as 4, 2 from light holes and 2 for heavy holes. So at 300K, all dopants are ionized. So we can write Nd plus as Nd and Na minus as Na. So it becomes P plus Nd equals to N plus Na. So And now we have mass action law, which gives at thermal equilibrium Np equals to Na square, that is P equals to Na square by N, which we substitute here, we get Na square by N minus Nd minus N plus Nd minus Na equals 0. By assuming full annihilation and applying the mass action law, we compress the chaotic reality of the lattice into a pure quadratic expression, solve it purely for N. The ingenious flowchart for correct calculation. So are you in the extended region? You calculate the quadratic formula. So, so if you can go for quadratic formula, you have a massive square root equation that needs to be solved. So what is the shortcut? You assume, you see if Nd minus Na is greater than Ni. If yes, the Ni terms is mathematically invisible. So N type Na becomes so assuming it is N type, N becomes Nd minus Na, and holes will be P equals to Ni square by N, which is Nd minus Na. Or it is also possible that there is no countered opening, that is N equals to 0, only Nd is available. Then it's even simpler, N equals to Nd and P equals to Ni square by Nd. This final simplification is why precisely doping works. We can dictate the exact number of free electrons simply by counting the physical donor atoms we implant. So semiconductor doping is not just chemistry, it is an exploratory geometry. By leveraging the vast difference in energy gaps, we isolate a thermal window where electrons behave perfectly according to our mathematical design. And this plateau is where modern semiconductors operate, and this is where which allows us to create computation logic. Now we come back to our PPT. So now I will be showing you some practice questions. If you have to solve this. If you have the answer, you can write in the chat or speak your answer through the microphone. First question. Which of the following represents the correct volume occupied by a single allowed state, including spin degeneracy, in a three-dimensional reciprocal case space for a semiconductor crystal of macroscopic dimensions Lx, Ly, Lz under periodic boundary conditions? Pi cube by Lx, Ly, Lz, 4 pi cube by Lx, Ly, Lz, 8 pi cube by Lx, Ly, Lz, 4 pi cube by 3 Lx, Ly, Lz. So the answer to this is option B. So in 3D space, the allowed wave vectors are given as Ki equals to 2 pi Ni by Li, where Ni is an integer. Thus, the reciprocal space volume occupied by a single orbital spatial state is 2 pi by Lx, 2 pi by Ly, 2 pi by Lz, that is 8 pi q by Lx, Ly, Lz. And if we apply the spin degeneracy, then each orbital state can hold two electrons. Consequently, the reciprocal space volume per spin tangent electron state is half, making it 4 pi cube by Lx, Ly, Lz. For a two-dimensional electron gas confined in a quantum well of area A equals to Lx Ly, what is the exact density of states in K space Gk of K per unit area accounting for spin degeneracy? K by 2 pi, K by pi, K square by 2 pi, 1 by 2 pi square. The answer to this would be K by pi. So in 2D, the area of a circle in K space is radius K is pi K square. Under periodic boundary conditions, the area per state in K space is 2 pi by Lx, 2 pi by Ly, 4 pi square by 8. So the total number of spatial states within a radius K is 8k square by 4 pi. And for spin degeneracy, it will become ak square by 2 pi. And when you go for per unit area, it becomes 1 by 8 to d nk by dk, which is k by pi. In the derivation of the 3D density of states, the transformation from wave vector space K to energy space E relies on a parabolic dispersion relation. Under what physical condition does this approximation Ek equals to Ec plus h bar square k square by 2m star fail in real semiconductors? Deep within the band gap where no states are present, highly degenerate doping or high energy excitation where carriers occupy states far from the conduction band minimum Ec, low temperatures near absolute zero where the Fermi function becomes a step function, in intrinsic semiconductors where the electron effective mass equals exactly equals the whole effective mass. So the answer to this will be the parabolic dispersion relation is a Taylor expansion of the band structure Ek around the band extreme, that is conduction band minimum or valence band maximum. This approximation is highly accurate for low energy carriers near the band edges. However, highly degenerate doping or high energy carrier concentrations. Carriers occupy states deep in the conduction band or valence band. In these regimes, non-parabolicity effects become significant and the dispersion relation deviates from the simple quadratic k-square dependence, causing the parabolic density of state models to fail. How does the density of state G of E scale with energy E related to band age for 3D, 2D, 1D, and 0D systems respectively? Option A, G3D is proportional to E per half, G2D is proportional to E0, G1D is proportional to E minus half, G0 is proportional to delta E. Option B, G3D is proportional to E per minus half, G2D is proportional to E0, G1D is proportional to E half, G0D is proportional to E1. Option C, G3D proportional to E1, G2D is proportional to E per half, G1D is proportional to E per 0, G0D is proportional to delta E. Option D, G3D is proportional to E per 3D, G2D is proportional to E per 1, G1D is proportional to E per half, G0D is proportional to E per E. So the correct answer is option A. So the energy scaling for the density states as a function of dimensionality is a fundamental result of solid state physics. For 3D Bird semiconductors, G of E is proportional to E minus EC per half. For 2D quantum wells, G of E is proportional to E minus EC per 0, a staircase function with constant step heights. For 1D quantum well, G of E is proportional to E minus EC per minus half, exhibiting singularities that are Winehouse singularities near subband edges. For 0D's quantum dots, the DOS is a set of discrete energy levels represented by direct delta function. G of E is proportional to delta E minus En. A gallium arsenide quantum well 2D system has a thickness of Lz equals to 8 nanometers. The conduction band effective mass of gallium arsenide is Me star equals to 0.067 m naught. Calculate the constant density of states per unit area G2D for the first subband in units of m cm minus 2 per cm square per electron volt. Use m naught equals to 9.11 into 10 power minus 31 kg. H bar equals to 1.054 into 10 power minus 34 joule seconds. Option A 2.85 into 10 power 13 per centimeter square electron volts. Option B equals to 2.84 into 10 power 14 per centimeter square electron volts. Option C is 5.7 into 10 power 13 per centimeter square electron volts. Option D is 5.7 into 10 power 14 per centimeter square electron volts. The correct answer is option A. So the 2D density of states per unit area is given by G2D equals to m star by pi h bar square. So if we put all these formulas here, so m star is given as 0.067 m naught. So we put there pi we know, and h bar is given as 1.054. So calculate all that, you get 1.7489 into 10 power minus 30, 10 power 36 joule inverse meter per joule meter square. So we convert this to meters per meter square electron volts, and from there we convert it to centimeter square, which gives us around 2.8 into 10 power 13 per centimeter square electron volts. Consider a 0D semiconductor quantum dot. Which of the following statements best describes its density of states and the optical transitions that can occur? The DOS is continuous and parabolic. Optical absorption occurs over a broad continuous spectrum. The DOS is constant. Optical absorption exhibits a step-like structure. The DOS consists of discrete sharp energy levels represented by delta function. Optical absorption exhibits sharp delta-like peak features similar to atomic transitions. The DOS is linear. Optical transitions are forbidden due to coordinate symmetry rules. So the answer is B. Because a 0D quantum dot confines carriers in all three spatial dimensions, its quantum energy levels are completely discrete, resembling those of an isolated atom. This makes its energy of states a series of delta functions. G of E is equal to 2 sigma n delta E minus En. Consequently, optical absorptions and emission spectra of quantum dots exhibit narrow, sharp, peak-like structures at these discrete resonant energies, rather than the broad continuous absorption bands characteristic of bulk semiconductors. The Fermi-Dirac distribution function is given by f of e equals to 1 upon 1 plus e power e minus ef by kbt. At what energy E related to the Fermi energy Ef is the probability of finding an electron exactly equal to 10%, assuming a temperature of T equals to 300 K, which results in a kBT equals to 25.86 MeV. Option A, EF plus 25.9 MeV. Option B, EF minus 56.8 MeV. Option C, EF plus 56.8 MeV. Option D, EF plus 120.4 MeV. So the answer to this will be option C. So we said f of e equals to 0.1, which means 1 upon 1 plus e minus or ef minus e minus ef by qt equals to 0.1, which gives us e power ef minus ef by qt equals to 9, which means e minus ef by qt equals to ln 9, which is around approximately 2.1972. So that would mean E minus EF is 2.1972 into 25.86, which gives us 56.82. Under what mathematical and physical conditions is the Maxwell-Boltzmann approximation f of E approximately E minus E per E minus E per minus E minus EF by kT considered highly accurate, error less than 5% for the conduction band of a semiconductor? When the Fermi level EF lies deep inside the conduction band, that is EF minus EC greater than 3 kV. When the semiconductor is intrinsic and at absolute zero, that is T equals to 0 K. When the Fermi level EF is located in the band gap and at least 3 kV below the conduction band edge, that is EC minus EF greater than 3 kV. When the carrier concentration N is extremely high and the semiconductor is G-dented. So the answer to this will be option C. So the maximum Boltzmann distribution approximate f of E equals to 1 upon 1 plus E per EF minus EF by QBT approximately equals E power minus E minus EF by QBT. So this approximation requires the exponential term in the denominator dominate over 1, that is E power E minus EF by QBT greater than 1 for states at and above the conduction band E greater than EC. This is satisfied the lowest available state EC is far above EF, which is if it is greater than 3 kBT, then the minimum is E cube, which is approximately 20, which makes the relative error term equals to 5%. So this is highly accurate only when EC minus EF greater than equals to 3 kBT. At what temperature T in Kelvin will the Fermi direct probability of an electron occupying an empty state at E equals to EF plus 0.1 eV be exactly 15%? Use Kb equals to 8.617 into 10 power minus 5 electron volt per Kelvin. Option A 116 Kelvin, option B 300 Kelvin, option C 674 Kelvin, option D 1160 Kelvin. So correct answer to option C. So we said f of e equals to 0.15, and we know e minus ef is 0.1 ev, and we know so this will give us 6.677, e part 0.1 by qt equals to 5.6667. So from here we can get temperature approximately 669 Kelvin, which is roughly 674 Kelvin. In N-type doping, donor impurities introduce localized states within the band gap using Bohr hydrogen atom model. How does the ionization energy of these donor states scale with the semiconductor's dielectric permittivity and the electron's effective mass m star? Option A, ED is proportional to m star by epsilon r. Option B, ED is proportional to m star by epsilon r square. Option C, ED is proportional to m star square by epsilon r. Option D, ED is proportional to m star epsilon r square. So the correct answer is option B. The ground state binding energy of an hydrogen like donor atom in the semiconductor crystal is modified from the standard hydrogen model by replacing the free electron mass with the effective mass m star and replacing the free space permittivity epsilon naught with the semiconductor permittivity epsilon naught epsilon r. This yields ED equals to EH m star by m naught into 1 by epsilon r square. Therefore, the donor energy, hydrogen energy scales as ED is proportional to m star by epsilon r square, which is option B. Calculate the donor binding energy ED in MeV for silicon using the hydrogenic model. Assume the electron effective mass in silicon is m star equals to 0.26 m naught and the relative permittivity is epsilon r equals to 11.7. The ground state energy of a hydrogen atom is 13.6 eV. Option A 1.25 MeV, option B 25.8 MeV, option C 136.2 MeV, option D 302.3 MeV. So the correct answer is option B. So the hydrogenic model gives us AD equals to 13.6 into m star by m naught into 1 by epsilon r square, where we are given m star by m naught is 3.26 and epsilon r is 1.7. We get ED equals to 0.02583 eV, which is 25.83 milli eV. This matches typical donor radiation energy silicon, such as for phosphorus, which is around 45 MeV, which is close to this simplified theoretical estimate. Uh, At T equals to 300 K, what is the critical electron concentration index in N-type silicon above which the semiconductor becomes degenerate? Assume the Fermi level must be exactly at EC minus 3 kBT at this threshold. For silicon at 300 K, NC equals to 2.8 into 10 per centimeter cube and kBT equals to 25.86 MeV. Option A 1.39 into 10 per 18 per centimeter cube. Option B 2.8 into 10 per 19 per centimeter cube. Option C 5.62 into 10 per 20 per centimeter cube. Option D 1.39 into 10 per 21 per centimeter cube. So the answer here would be option A. So under the Boltzmann approximation, the electron concentration is given by N equals to NC E per minus EC minus EF by kBT. At the threshold of degeneracy, EC minus EF equals to 3 kBT, which means N dag equals to NC E per minus 3. Substituting it, we get N dag equals to 1.0 10 per 18% vacuum. Above this concentration, the Boltzmann approximation starts to introduce significant error, and the semiconductor is classified as degenerate. The ionized donor density is given by Nd plus equals to Nd upon 1 plus Gd e per EF minus Ad by kBT. What is the physical origin of the donor degeneracy level? Gd equals to 2. It accounts for two possible directions of spin, up and down, for an electron occupying the donor state, coupled with the constraint that the donor state can hold at most one electron at a time. It accounts for double value degeneracy in the conduction band minimum of semiconductors. It represents the dual coordinate state of the reciprocal lattice. It is a correction factor due to relativistic strain orbital coupling of valence band. The answer to this would be option A. So donor level can be empty, positively charged Nd plus, or occupied by one electron, neutral Nd0. Because of spin tendency, the electron can spin up or spin down, meaning there are two distinct states for an occupied neutral donor. However, the donor cannot accept two electrons simultaneously because the strong Coulomb repulsion between two electrons localized on the same donor atom makes that state energy extremely high. This asymmetric constraint, two ways to be neutral but only one way to be ionized, alters the statistical partition function, introducing the degeneration vector GD equals to 2 in the denominator. For acceptor states in silicon and germanium, the degeneracy factor is typically Ga equals to 4. What physical characteristics of the valence band structure causes Ga to be 4 instead of 2? The heavy hole and light hole valence bands are degenerate at the zone center, a lambda point, and each band possesses a two-fold spin degeneracy. The split of band adds two extra degrees of freedom. Silicon contains 4 valence electrons in its outer shell. There are 4 distinct equivalent coordinate systems in a diamond crystal structure. And the answer to this is option A. In many cubic semiconductors such as silicon and germanium, the valence band edge consists of two bands that are degenerate, have the same energy at the zone center, that is K equals 0. The heavy hole band and the light hole band. Since each of these two bands have a two-fold spin degeneracy, spin up and spin down, there are a total of 2 into 2, 4 degenerate valence band states. When an acceptor captures an electron to become ionized, this band degeneracy must be reflected in the occupancy statistics, resulting in an acceptor degeneration factor of Ga equals to 4. In a silicon sample at T equals to 300K, the donor concentration is Nd equals to 10 per 16 per centimeter cube, with Ec minus Ed equals to 45 milli electron volts. If the Fermi level Ef is situated exactly at the donor energy level, that is Ef equals to Ed, calculate the percentage of donor atoms that are ionized, that is Nd plus by Nd. Assume Gd equals to 2 and Kbt equals to 25.86 MeV. Option A 33.6%, option B 50%, option C 66.7%, option D 95.2%. So the correct answer would be option A. So the fractional of ionized donors is given by Nd plus by Nd equals to 1 upon 1 plus Gd e power Ef minus Ed by kBt. Given Ef equals to Ed, the exponential term becomes Ed equals to 0, which means Nd plus by Nd equals to 1 upon 1 plus Gd equals to 1 to 1. That is 1 by 1 upon 1 plus 2, which is 1 by 3, which is 33.3%. Thus, only 33.3% of donors are ionized and 66.7% remain neutral, that is unionized, under this specific Fermi level condition. The plot of the natural logarithm of electron concentration versus inverse temperature 1 by T is commonly used to analyze doped semiconductors. What are the slopes of this curve in the freeze-out regime and the intrinsic regime respectively? Slope in freeze-out regime is minus Ed by Kb and slope in intrinsic is minus Eg by Kb. Slope in freeze-out is minus Ed by 2 Kb. Slope in intrinsic is minus Eg by 2 Kb. Slope in freeze-out is 0. Slope in intrinsic is minus Eg by 2 Kb. Slope in freeze-out is minus Eg by 2 Kb. Slope in intrinsic is minus Ed by 2 Kb. So the answer to this is option B. So the low temperature freeze-out regime, carrier concentration is dominated by the ionization of donors. The concentration is proportional to E per minus Ed by 2 kT, which gives a slope of minus Ed by 2 kb on a ln n versus 1 by T plot. In the high temperature intrinsic regime, the thermal band-to-band excitation dominates over dopant atoms, that is Ni is greater than Nd, and the concentration scales as Ni is proportional to E power minus Eg by 2 kBt, which yields a slope of minus Eg by 2 kb. In the intermediate extrinsic regime saturation, nearly all dopants are ionized, making N independent of temperature results in a slope of approximately 0. Starting from the general charge neutrality equation P minus N plus Nd plus minus Na minus equals 0 for a non-degenerate semiconductor at room temperature, assuming complete ionization Nd plus equals to Nd and Na minus equals to Na. What is the exact mathematical expression for the electron concentration N in terms of Nd, Na and Ni? N equals to Nd minus Na by 2 plus square root of Nd minus Na by 2 whole square plus Na square. N equals to Nd minus Na by 2 minus square root of Nd minus Na by 2 whole square plus Na square. N equals to Nd minus Na plus Ni. N equals to square root Nd Na plus Na square. The correct answer will be option A. Assuming complete ionization, the charge neutrality equation is P minus N plus Nd minus N equals 0 from the mass action law P equals to Ni square by N, which gives us Ni square by N minus N plus Nd minus Na equals to 0. If we solve this for quadratic equation, we get N equals to Nd minus Na plus minus square root of Nd minus Na square minus 4 into 1 into minus Na square divided by 2, which gives us N equals to Nd minus Na by 2 plus square root of Nd minus Na by 2 square plus Na square. Only the positive root is physically meaningful, so its carrier concentration must be positive. So we cannot have the negative value. A silicon sample is compensated such that it contains Nd equals to 10 per 16 per centimeter cube donor atoms and Na equals to 8 into 10 per 15 per centimeter cube acceptor atoms. If the intrinsic carrier concentration is Na equals to 1.5 into 10 per 10 per centimeter cube at 300 Kelvin, calculate the exact electron and hole concentration in the sample. N equals to 10 per 16 per centimeter cube, P equals to 8 into 10 per 15 per centimeter cube, N equals to 2 into 10 per 15 per centimeter cube, P equals to 1.125 into 10 per 5 per centimeter cube, N equals to 2 into 10 per 15 per centimeter cube, P equals to 1.5 into 10 per 10 per centimeter cube, N equals to 1.8 into 10 per 16 per centimeter cube, P equals to 1.25 into 10 per 4 per centimeter cube. So the answer to this is simple. Answer to option B. So this is a compensated semiconductor. The net active donor concentration is Nd minus Na, which is 10 per 16 minus 10 to 10 per 15, which is 2 into 10 per 15 per centimeter cube. Since Nd minus Na is greater than Ni, we can approximate N equals to Nd minus Na, which gives us 2 into 10 per 15 per centimeter cube, and then P would be Ni square by N, which will give us 1.125 into 10 per 5 per centimeter cube, which matches option B. So that is all I had for today. Thank you for attending the session. If you have any doubts, you can ask or you can leave the chat.